Next, we have Brett Kettering from Los Alamos National Laboratory. He's a computer scientist at LANL. He's in charge of software development, project management for HPC development environment tools and HPC file system I/O projects. Brett Kettering, please join me here on the stage and rock out. Thanks, man. Yours was a great abstract.
So, as Steve said, I'm Brett Kettering. I'm from Los Alamos National Lab, and I've been, among other projects, working on the PLFS development. We're trying to get it to a state where it could actually be used with a production code, and we're not quite there yet, but we'll go over that. I myself haven't done any of the major component development. I actually, every once in a while, dig into the code and find a bug or something like that, you know, some small stuff, but mostly I'm actually using it with our code teams and trying to see what it's going to take to make it work for them. So it's an effort that's been contributed to by quite a few people, including Megan, who just spoke. Megan used to work for LANL, and a lot of former LANL people have moved on to other companies. So this is the list of people that have been working on it. John Bent's also here. He's been one of the major code contributors. He's now working with EMC, and we have a CRADA with that company. They're doing some development with their engineering department. We have long-term partnership with Carnegie Mellon University, and one of their developers, Chuck Craner, has been actually a guy who's done a lot of work on PLFS, and some other people from academia have also contributed. And then Cray has an on-site person with our system Cielo, which this analysis was done on, and William Tucker is that person, and he works with their MPI team. They have to patch an MPI, and we'll talk a little bit about that because that's part of the process. So, at least at LANL, we have 3 primary I/O modes, and those are end-to-one and in 2 different flavors, strided and segmented. And strided end-to-one is where each process is writing their data, but they'll write a certain element like temperature or something like that, and then they skip down the line and write their next element. So in strided, it's organized by the type of data, so you might see all the temperatures together and so forth. And then segmented, each process gets a segment of that one file to write to. There's this mode that we call small file, and this development was actually done by EMC's engineering team and John. And there are some people at LANL that do this where they have one process that writes a whole bunch of really small files, and as you might well imagine, that can overwhelm a metadata server. And then finally, the flat file mode. A lot of codes do this end-to-end, where each process writes its own file, and primarily they've done that to get away from the traditionally poor performance of end-to-one on a parallel file system. So end-to-one, the problem, that's what really started the PLFS. And there were some primary issues there that you can see: excessive seeking and this region locking that was going on. And so there's a person at LANL who was sort of the father, if you will, of PLFS, and you know, he's a hardcore technical guy, and somehow has been roped into management, and he was found himself sequestered for a couple days at an offsite with a laptop and a wireless connection. And much like you all here, right? So he started thinking, you know, these guys have been bugging me for a long time about the poor performance of this end-to-one problem, you know, and I'm going to see if I can come up with a solution. And so he started writing code during this offsite management meeting for 2 days, and that was sort of where PLFS was born. And the idea was to use a log structured file to get rid of the excessive seeking. So, you know, just the writes would go sequentially into the file as they came from the processes, and that, of course, that order can vary because it's, in the end, it's sort of a race condition thing. You know, whoever gets there first gets their data in. And then the other aspect of that was this region locking. So if you had 2 processes going at the same file that happened to land on the same, in Lustre World OST, for example, unreliable, then they had to wait for each other on that lock. And so if you said, well, what we're going to do is convert this end-to-one file into end-to-end model, well, they no longer are contending with a competitor, and so they were able to get past that. Of course, now when you read the file, you have to consult this index, and that presents challenges, but at least in our world at LANL, what happens most is writing. And so there are a lot of writes happening, and a read only happens when the application's restarting. So this is graphically what an end-to-one strided looks like. You know, each process has got its data, and you know, you can kind of, if you just follow the red guy, you'll see how the red boxes jump down the line there as they write the elements of their file out there. And so what PLFS does is say, oh, well, now we're just going to take all you red guys and put you in your own file, and orange guys and so forth. And there's a directory hierarchy, and we'll get to that also. There is an overhead, obviously, to doing this, and I'll show you what the overhead is for each of these modes. So the one-to-end file situation, again, this is where, you know, like files or processes are writing sometimes tens of thousands of files each, and there may be, kilobytes in size. And so if you're creating a file, writing just a few kilobytes, syncing and closing, you're doing a lot of file management overhead for very little data, and so you get killed by the overhead. So you need to find a way to amortize that overhead over more data, and so essentially what one-to-end does is says, okay, if that's your model, you can just go ahead and keep writing like that, but what we're going to do is create one file, and we're going to log file mode all this data into a single file, and then we will keep track of the offsets of where you tell us each of these files belongs. And so that's what this looks like, where you're writing a whole bunch of files, and as you can see, it turns into one file with a bunch of data in there, and the files logically represented. And then, of course, you can't just tell a bunch of codes, hey, you know, if you do end-to-end, you can't use our file system. So we have to support it, and we do. And so the one thing that PLFS does for you, though, it's not really such a big deal right now, because most codes don't create or don't have so many processes that it overwhelms a directory, but it will spread these files out over multiple directories. And some codes, I know Ruth from Sandia, I know a couple of Sandia codes have a mode implemented where they can also do that for themselves, right? They will spread their files out over multiple directories because they've run into the problem where they created so many files that they could then no longer really effectively access them. So PLFS will do that for you. You don't have to worry about that in your own code anymore. And this is what it looks like from a PLFS mode. We just create directories on various file systems and then distribute the files over them. Okay, so there are three ways that you can use PLFS. First one is using MPI-IO. So most of our codes are MPI codes, and they'll do the standard MPI file open, and then they start writing to it, and then they do the MPI file close. So we decided, well, we got to support that model, and we need to make it as seamless as possible, but we had to make you do one thing, and that is prepend the text PLFS : to the file's name when you open it, and that way we branch into a portion of the MPI code that we patch, and then it can call the PLFS API to do the I/O for you in that manner. So the mount point doesn't have to exist on the system itself. So if you were to go on to log on to a system and do a DF and or mount and look at the mount points, you wouldn't necessarily need to see a PLFS mount point in order to use the MPI-IO mode, but it has to exist in this file, which we call a PLFS RC file, and that just tells it where the actual physical locations are that this file system is going to use. So that has to be there. FUSE is another interface we have. So this does require an actual mount point that you would see if you were to do a DF or a mount on your system, and again, that file mount point is defined within the PLFS RC and tells it where the physical locations are. This is for people who want to go in and LS their files or remove them or move them. archive them potentially, and it can, there's a note here that says that there's a performance overhead, and I wrote that before we made this discovery about the buffer sizes of, that FUSE uses by default and how to get around that problem. But if you're doing sequential mode stuff, it can still result in an overhead. We use, at LANL, we use these systems that we call FTAs, file transfer agents, and we increase the threading capability of PLFS so that when you do, for instance, a remove, which you're actually then removing a whole bunch of files underneath the covers, it can do that in parallel rather than sequentially with a single thread. So it's good for you to think about that. If you're going to use PLFS, you may want to tell your users when you're moving files around, when you're copying files around, when you're removing files, archiving files, use these special nodes that we've set up to increase the threading, and you'll get better performance. And then finally, there's an API for PLFS, and so that's the biggest change. If you want to do your code that way, then you're going to have to go in and replace any sort of POSIX call or any MPI call that does file manipulation with the corresponding PLFS call in the API. Good performance, but more intrusive. Okay, so the overhead for the end-to-one, that depends on the mode that you use. And MPIIO, I've listed all the files here for you, and so basically all but the last two sort of vary depending on configuration parameters, but you could think of that as a small constant amount of files that get created. And then basically it's a 2N data, because there's a data file and an index file for each writer process. So you're creating two files for every one file, or for every one process that you have involved in it. If you use PLFS FUSE, it's slightly different. There's a data file for each writer process, but there is an index file for each node. And on Cielo, for example, the system that you'll see the data with soon, that was 16 processors per node. So you have a slight reduction in the overhead because the index file overhead goes down. And then finally, the PLFS library, it's actually a 3 times N overhead. So there's the data file, there's an index file, and then there's a metadata file that's there for each process. End-to-end and one-to-end file overhead is listed here, and if you do end-to-end, we actually recommend you use multiple backends versus when you do one-to-end, we ask you to use one backend per file system, and then you have basically no file overhead. It just creates a file for every file, and there may be multiple directories created depending on how many backends you have, but typically people create their backend, their directories that they're going to write files into before the actual application runs, so that overhead was done offline, if you will. And then one-to-N, again, there's overhead, and it's about a 3-to-1 overhead. Also, there's the data file that gets created. There's an index file that has an integer index that maps the particular file to a location. And then there's a map file that says, well, what's the actual name of that file? So those are the files that exist to track all this stuff. Okay, so we recommend you use PLFS for very large parallel file I/O, primarily N-to-1 and one-to-N. N-to-1 is in the best shape at this point. One-to-N code we're still working on. And you need to do a lot of work in order to amortize the overhead over there. And so when you're writing large files like restart dumps for simulations or graphics dumps and so forth, those are usually your candidates. You don't want to deal with a lot of small files that are, that are your problem inputs and log files that your application creates and your executables and so forth. You don't want those really on PLFS. You use your projects or NFS type file systems there. In the small file mode, it's not completely POSIX compliant, so you have to be aware of that. It's not because that's how it gets performance, is by caching everything locally. So if you're going to write a whole bunch of files and then you want another node, for example, to be able to read those files, you have to do an explicit sync to get those flushed out to storage and then be able to look at them. And then finally, avoid the read-write open flag. for PLFS files. As you might imagine, out of necessity, if you do a read-write file, every time you go to read it, PLFS has to go back and read that whole index again so it knows where the parts and pieces of your file are, because it could have potentially changed while you were doing that. Again, for our simulations, that's generally not a problem because they're either reading the file or they're writing the file, and so we don't really have that much of an issue with our code teams. And then, this is irrespective of whether it's PLFS or not, but we constantly are reminding our code teams, don't stat your files while your simulation is running. They'll sit there and do ls minus L all the time to see if their file's growing. That's bad. All right, so we did some testing. FS test is basically LANL's version of IOR, and it's sitting out there on GitHub, so if you want it, there's the URL. You can go get this code. The one thing that's kind of nice about it for us at this point is it actually has the PLFS API integrated into it, which IOR doesn't have at this point. So we use this code to run basically maximum bandwidth throughput tests for our systems, and in this case we ran these tests on the ASUS Cray, which is called Cielo. It has 3 Lustre scratch file systems that are L-Scratch 2, 3, and 4. 2 and 4, if you will, are quarter-sized file systems, and 3 is a half-sized file system. All totaled, it's about 8 petabytes of usable storage. So 2 has 2 petabytes, 3 has 4 petabytes, and 4 has 2 petabytes worth of storage available to it. And for the end-to-one runs, we were unable to get the 32K and 64K PE runs because I don't get special time on this machine. I just kind of have to sneak in as I can and get processors when I can. So here is the end-to-one and end-to-end performance with PLFS and non-PLFS for writes. And so we just wanted to make sure that we were there in the ballpark, right? So if somebody used the end-to-end model, we didn't want to really make them suffer too much. And as you can see by the first 2 bars, that our end-to-end performance actually in some cases was slightly greater than the normal end-to-end, but it's right there in the ballpark all the time. And then the right 2 bars in each clusters are the end-to-one mode. So it's the really low ones are the normal end-to-one mechanism that people would use, and then the blue bar there is end-to-one through PLFS. And as you can see, what it does is it jumps it up to near end-to-end performance. And so this was done with FS test, writing huge chunks of data at a time so that we were trying to, amortize away all the open, sync, and close overheads, and just to see what we could do. And it looked good. And that's the read performance in a similar method. So that's always fine, well, and good. We used a benchmark tool and got good performance, and people say, so what? Run my real application. So, okay, we did. There's a project called Silverton there, and it's a 3D Eulerian code that does finite difference stuff. It's all compressible flow. Physicists will understand this stuff. To me, it's just like words I pulled out of their description of what their code does, and I know how to run their code. And so we ran it first of all with one of their smaller test problems, and we wanted to see what that would do and use their normal end-to-one mode. And they have several modes that they support. They have end-to-one strided, end-to-one segmented, and they have end-to-end also. And so we ran it against the L-Scratch 3 on Cielo, competed against other jobs running there. And this is what we saw on the small problem for their end-to-one mode, strided writes. We got about 1.7x increase over the write. So, that was good news, right? It certainly wasn't the 4x increase that we saw with our little benchmark application, but this is a real app and doing I/O the way they really do it, and so that was telling that it did better. Reads, it wasn't quite as good, but it did a little bit better on the reads. So after that, we had this small problem. We decided, well, let's jump to a big problem. And by the way, this small problem we run at 32K processors all the time, but I don't remember exactly how much data it was. It's in a paper that I wrote, but it was in the gigabytes range, small gigabytes. And so we jumped up to a bigger problem that we ran at 512 processors and 4K and 32K processors, and 32K processor job ended up with a restart file that was 2.2 terabytes in size, and it was scalably smaller as you went down in the processor speed. So at the low processor count, you have to look at these in pairs. So if you start, let me see if I can use this. That one is their normal N-to-1. That's PLFS on their normal N-to-1. That's their N-to-1 segmented, and that's the purple is, PLFS on their N-to-1 segmented. This is their N-to-N, and then that's PLFS on their N-to-N. The really important part is over on the far right cluster at 32K, because we're, again, telling people this is for scale, right? That's where you're going to see the benefits. And you can see that in the N-to-1 modes, both strided and segmented, PLFS did really well on their I/O problem, and it was in the ballpark of comparing to their end-to-end their model. So if they used end-to-end, they wouldn't suffer too greatly. But this is a code that typically does use the end-to-one model. All right, so we went to another project that's EAP. It's the Oil Area and Applications project. For those of you labbies, it's formerly Crestone, if you know that project. And they have a 3D solver that does an oil area mesh with adaptive mesh refinement. We had a really nice end because Megan's dad works for them. And so he was willing to help us out. It's amazing what fathers will do for their daughters, right? He taught us a lot about how the code worked and their typical problems that they like to run, and then turned us loose, and we ran some problems there. And they have this favorite little problem of theirs called the asteroid problem, and so we ran that one first of all. Because whenever you talk to the EAP project, they want to know how to do on the asteroid problem. And so we did that, and then we went to a really large problem that they had that we called the MD, and it just happened to be the initials of the original scientist that was doing it, and then another developer who was helping him out when they were having some problems, whose name's Marcus Daniels. And so this was a 23 terabyte restart dump, and so that was a really fun one to play with because it was a huge file, right? It was the biggest restart dump that anybody had done at LANL up to that point. So again, we were competing with, I guess I should, how much time do I have, Steve? 15? Okay, so the EAP project in particular has recognized this issue that they have with N-to-1, and they have a custom I/O model called bulk I/O that's mentioned here. And they've spent a lot of time working on this to make it work for various file systems. And what it does is it decides, what the underlying file system is and how it's all built. And in the Lustre case, what they've said is, we're running Lustre 185, or 4, sorry, on Cielo. And there's limitation to the number of OSTs that you can have. And I think that number is like 180, if I recall correctly. So the EAP didn't want to use all of those, so they said, well, we'll pick 160 of those. And then the way bulk I/O works is they designate 160 of their processors to be the writers, and then they aggregate all data from the other processors to the writer, and then they write huge chunks at a time and try to get the best performance that they can. They did a pretty good job with it, and so we thought, well, that'll be a good comparison for PLFS, which is just taking their normal MPI I/O in the N-to-1 model as it comes and converting it to something that we think will work better on the underlying file system. And so we didn't do, hugely better than them on the maximum write. I'm showing the maximums here because, again, we're competing with normal jobs running, and it appeared to me when I looked at the results, we had several runs that it looked like several of the runs got caught with bulk I/O runs by competing with other jobs, and so the averages look kind of low. So we thought, well, let's look at the maximums. That would be a telltale assigned to us about what we could expect the best that this could do. So you can see we're a little bit better than bulk I/O, and almost twice as good as their normal MPI mode. And their normal MPI mode is what we use as a feeder into PLFS. And so we thought, okay, well, that looks good. And so we did the read. And their MPI mode actually was ballparkish with us, but we did a little bit better in the read. And then we went to this big problem. And the big problem was really interesting to us because that's where this code team is going, is to these huge problems. And so we ran that code with the bulk I/O model, and that's the blue bar, on a smaller one of the scratch files, and then, because that was what was available to us. And then we ran the PLFS version, which is the red bar there, and we did about 1.5x their performance. And I just wanted to see, when I got some time, what would happen with their bulk I/O model if I got them to the bigger file system, got them a little more hardware to work with. And they did better, as you can see in that green bar, but they still weren't even equal to what PLFS got on a half the size file system. So one of the advantages that PLFS has also is that you can combine multiple file systems into one virtual file system. And this is all invisible to the user. Again, they're just going to open a file on a file system designator that you give them. And that's what the purple bar is. We combined all three of Cielo's file systems, LScratch 2, 3, and 4, into a single file system, so they had access to the whole set of hardware that we have on Cielo. And we ended up getting 3 times the performance that bulk I/O got on LScratch 3. But to be fair, you have to say, well, let's say that, it scales linearly and you doubled the size of the file system underneath bulk I/O. We were, again, 1.5 times their performance. So that's sort of what we settled on in the PLFS world. We're saying right now, give us somebody's normal N-to-1 mode, and we think that we can do about 1.5 times better than what they're getting. All right, so we did a read also, and read really didn't benefit that much from combining all the file systems, but it did okay. There's more work to do, and so in order to use this as a capability that somebody's going to rely on every day for every run and know that they can get their data back and analyze it in the future, it's got to work for them all the time. There are a couple issues that we've been working on. One is, many of you may know this, but FUSE buffers are defaulted in size to 128 kilobytes, which is very small, especially in our world. And unfortunately, it's also hard-coded. So if you want to change that, you actually have to change an include file in the kernel source, and then some actual source code in the FUSE kernel module itself, and just to bump it up. And we did that and changed it to 4 megabytes and saw that we got a lot better performance. We did this when we were trying to archive and saying, can we pull these files off of a PLFS file system and stick them onto HPSS, and then vice versa, pull them off of HPSS, put them back on there, because that's something that our users are going to want to do every day. And it turned out that it was horribly bad performance when the FUSE buffers were at 128 kilobytes. But when we bumped them up to 4 megabytes to match the archiving tool that we use, which is called HSI, then we were getting actually better performance from anywhere from 1.36 to 2.39 times the performance, depending on the file size, of HSI from a normal Lustre file system onto HPSS. And we're pretty sure that the reason for that is, as I mentioned, on these file transfer nodes we use threading. So we have multiple threads transferring parts of the file concurrently, whereas Lustre doesn't do that. So there's this FUSE issue to work through. And I actually just got an email while I was here from one of the admins telling me, it looks like the memory just keeps growing on the node that we've patched. So we've got problems to work on there. We can't have that. You can't have every time you do a transfer, just consuming more and more memory until finally the machine's out of memory and reboot it. And that'll happen daily if we do that at LANL. So we've got some work to do there. The other thing is, I mentioned the indexes, right? So PLFS has to maintain these indexes to tell you where your data physically resides on the file system when you ask for it from its logical location in the file. And currently what happens is every process involved in the read reads the entire index because they don't know which part of the file they're going to be asked for. And with that MD problem that I mentioned, which is 23 terabytes, it turned out that the index was more than 750 megabytes per process. And so by the time each process loaded that index and then started to read the data that they were responsible for into memory, well, each process exhausted memory and the program couldn't continue. We came up with a workaround to actually do the reads just so we could see what sort of performance we get. But on a day-to-day basis, we're going to have a scalable way to deal with the indexes. And there is a project that's been going on called MD-HIM, and that is a hierarchical index management. Well, I'm sorry. It's a key value store, and we use it for index management. And so we'll be able to not have to load all the indexes into memory, and it's a distributed mechanism. So if a process says, well, I need to read from offset X, and I need so many bytes, it then just asks the service, where is this file? And we'll be able to find it. So it's only going to load into its own memory at any one time the index information for the current read that it's trying to do. And that should be scalable. So that is all I have for PLFS. So if there are any questions.
So, one, where do I get it? And two, why use Lustre?
Well, why did I use Lustre? Because that was the file system that our Cray has. I mean, it'll work on Panasas also, or GPFS, but our organization is going in the direction of Lustre. And I'm sorry, I missed the first part of your question.
So where can I get PLFS?
I should have put that up there. It's on GitHub. So if you go to github.com, you can search for PLFS and you'll find it there. John?
PLFS, we call it a file system because it looks like a duck and it quacks like a duck, so we might as well call it a duck. As far as the user can see, it looks like a file system. But it's not a file system. It needs a real file system to do all the hard work that file systems do.
Right. It's an interposition layer, right? So it's doing a translation mechanism from how the application wants to do I/O to what the underlying file system wants to receive to do the best performance in I/O.
Okay, I'm stunned because 2.39 times performance of the underlying layer. Yeah, I guess I just didn't believe it.
Well, we threaded, we cheated, right? We had multiple workers doing it in parallel, whereas there's no way to tell Lustre, oh, hey, when you read this file, use a bunch of threads.
Okay, I'm relieved now.
Okay, you should feel better.
But Steve, it's a real problem. Shared file I/O is slower than file per process I/O. And that's why yesterday all these people were saying, hey, we did these benchmarks with file per process. And I said, why not shared file? And there's two reasons why when people benchmark, they don't show shared file. One, they don't care about it because their users aren't doing shared file. Or two, because the performance is lower.
Man, if I could teach our bio guys, how to aggregate files and use indexes, our lives would be, awesome.
You don't need to.
Nice. I'm stunned. Thank you.
The whole goal is to let the programmer do I/O the way they want to do I/O and not have to worry about the underlying file system, right?
What, let people do science?
Well, even programmers. I mean, there's a guy that works for EAP that his whole job is just handling their I/O model, right? Their bulk I/O. That's his whole job. And if they could free that guy up to do, physics development, they'd probably be very happy, I would think.
Cool.
So, Brett, quick question for you. So, PLFS adds some additional overhead on the compute node client, right? And as we start scaling out and potentially get lighter weight compute nodes, or lighter weight cores at least, potentially on some future architectures, would there be an opportunity to integrate what you've done here with an I/O forwarding layer so that these services could potentially reside on an I/O forwarding node?
Yeah, I'm not involved with that effort, but there is a, what do they call it now, fast forward effort going on right now that's doing just that, actually, using IOFSL. And John, are you involved with that? Yeah, okay. So EMC is involved with that, and Intel, maybe? But I have not been involved. My job has been, get this working for a code team like EAP. So, yes?
Can you elaborate on the, expected date when the, it will be in full production? When these bugs will be fixed?
All those people's names that you saw listed on that second slide are all part-timers. I think Alfred is probably the most, he's half-time. I'm not, I'm 4/10 time on this project. So it's kind of going along slowly. In order to use it for EAP, the problem that we need to solve right now is this scalable index thing. And we're right now in the process of, we have just hacked an interface to MDM right into PLFS. It's not the interface that we're going to end up with, because it's not well implemented in a computer science way. Right now it's just to get it to try it, right? And if it looks good, then we will go back and computer science-ify that interface and make it solid. I think if that index mechanism works, you're probably looking at what we call the end of our fiscal year, so it's going to be like October 2014, before we would probably feel comfortable using it with a production code team. And that also depends on the state of the MD-HIM code, which is very new also. So that could slip based on the readiness of MD-HIM.
Okay, thank you.
It's just all being done sort of in a bunch of people's spare time right now.
Okay.
But if I may say a word, we encourage everybody to try it.
Sure, yeah, try it, and you can submit bug reports, and we'll look at them. Yeah.
Just a quick question. Do you have a list of pain points for parallel file systems, a list of requirements, the things that we can put into Lustre that would make PLFS go fast?
You mean like configuration parameters for Lustre? Is that what you're saying?
Just what are some of the problems you have with parallel file systems underneath PLFS? What features, or what would do you have a list of things that would be nice to have to make the scalability work a little bit better, the performance a little bit better?
No, I mean the underlying file system works pretty well. We do is tell you, like, when you're doing end-to-one, you should use only one back end, because if you try to distribute the end-to-one model over a whole bunch of back ends, you're sort of defeating the purpose. And so we say, if you're going to use the end-to-one model, when you define your PLFS file system in the PLFS RC file, use a single back end per file system that you use. So like when you saw the note there where I used LScratch 2, 3, and 4, I had one back end on each one of those file systems, so that when PLFS picked the location, it was a single location on each file system that was going to, and just deals, it just looks like N files that you're shoving off to that file system with some directory creation and so forth. John?
Another question you might ask is, what could you do in Lustre to render the need for PLFS, render PLFS unnecessary? And that's when you do these benchmarks, show the difference between file per process and shared file. And they close that gap, and then, Los Alamos will take all of these people and they have to actually do science instead of computer science.
That's shown.
Yeah. So, I mean, the one thing that has, worked kind of well, if you look at those benchmark numbers that I gave in there that were for just the normal MPI, what Silverton calls MPI independent, MPI IND, a normal MPI mode. You stripe the file over a whole bunch of OSTs, right? And so with the 2 version of Lustre, that number gets bigger. You can stripe it over more OSTs. So the performance for just straight Lustre wasn't too bad when you could widely stripe.